Today we are detecting and studying intermods using an SDR receiver. Intermods are affecting you more than you think. In an earlier video, we derived how intermodulation products are caused and how they can be avoided. Feel free to watch the video. Today we are studying intermodulation products further. Using an SDR receiver, we are showing how to track down the cause of intermods, and we will demonstrate some interesting effects. I've been looking quite a while for practical examples where you can really hear and see intermodulation products. I like the RSP-DX because I can use 3 switchable antenna inputs to compare my homemade antennas. However, for the following experiments, you can use any other SDR receiver. I'll link you to some interesting devices below. I'm using a preview of SDR Connect, the new multi-platform software from SDR Play. A 75 cm lap cable makes a perfect antenna for the FM broadcast band. Practically all local FM radio stations are coming in, and I'm simply writing down the frequencies of the strong stations. From earlier episodes we know that 2 stations are theoretically causing 14 measurable products. With each additional station the number is growing exponentially. 12 stations are causing hundreds, and together with some weaker stations there are thousands. In our experiment, we don't want to analyze all products, but we keep this in mind for the interpretation of effects we will see in a few minutes. Third-order products are having relatively large amplitudes, and part of them are appearing near the fundamental frequencies. That's why we initially restrict our analysis to this category. These formulas are giving us an idea of all third-order products possible with 12 frequencies. But we are only calculating the ones of this type. This way, we don't get all possible products, but individual ones from the entire frequency range they can appear. I'm calling the series of our FM frequencies Fx. Then I put the same frequencies in a column calling them Fy. We are writing the results of all combinations into this table. About half of the 132 products is appearing in the FM band. We are turning up the RF gain to drive the preamp to its nonlinear range. The expected intermodulation products are actually superimposing the received signals. Within the FM band, intermods are a bit difficult to identify because we might confuse them with superimposed real signals. However, there is a suspicious indication that we will demonstrate in a few minutes. We don't want to get that far, but turning up the gain further, you might observe receiver blocking, pushing down practically all input signals. Have you ever thought about designing a printed circuit yourself? Here's a tip to get it produced in excellent quality for a fair price. Look at this, it's like a maker's dream, isn't it? Just check out PCBWay's websites. It's surprisingly easy. By the way, there are a number of further services that are interesting for makers. Take the easy way with PCBWay. The products outside the FM broadcast band are actually more interesting for our experiment. I want to look at the 70 MHz frequency range, as there is little activity otherwise on this frequency band. In this case, we have to consider FM stations as out-of-band interferers, and intermodulation is occurring on stronger signals only. Nevertheless, we can find the predicted intermod signals as soon as we turn up the RF gain. We can hear a mixed audio signal from 2 or more stations at the same time, and I can even identify which ones they are. This way, we can actually find the FM stations from which the intermods are called. Considering the RF signals are mixed including modulation, it is surprising that we can identify an audio signal at all. Why is that? Signals are retaining their modulation, including phase relations, when mixed. There is a mathematical proof for that. The principle is used for receivers as well as measuring devices, such as spectrum and vector network analyzers. The non-linearity of our preamp is actually mixing signals. The principle even applies obviously when you are mixing several modulated signals. In case of harmonics, however, things are a bit different. We need to discuss that in more detail in a separate video. Suppose we want to receive a weak signal in the 70 MHz range, then the intermods caused by broadcast stations could become really annoying. That's why the developers of the SDR receiver were adding notch filters for broadcast frequencies. Let's see what happens when we activate such a filter. Not only the third order intermods are disappearing, but the noise floor is also dropping significantly. Obviously, that noise is an intermodulation effect too. The enormous number of intermod products caused by many strong signals are adding up, forming that noise floor, which is dominated by the third order products. Incidentally, digital systems are suffering from intermods just as much as analog ones. However, the signals are not mixing up on the data layer, as the receivers can no longer decode the mixed signals. So you won't see mixed videos or so. Using the methods proposed in our video series, you can estimate suspect signals to identify the root cause, and you can try the measures proposed to avoid interference. We were provoking intermods on our SDR. However, receivers are sensitive to intermods in general. I can see them long before the preamp is indicating overload. Besides individual peaks in the spectrum, intermodulation is causing a kind of noise floor. Notch filtering of strong signals is reducing intermods really effectively. Now stay tuned and don't forget to support the channel. See you soon in the coming episodes.